Welcome you all. So in this lecture, we are going to see about the difference between ductile material and brittle material. Let us get into the video. So there are ductile material and brittle material. So we might have heard this word ductile material, brittle material in most of the time. So what is ductile material and what is brittle material? Why it is called as ductile material and why it is called as brittle material? So the ductile material will have the ductile property or the ductility, and the brittle material brittleness or the brittle property. So what is ductility? So ductility is the ability of a material to be drawn or plastically deformed without fracture. So it is therefore an indication of how soft or malleable the material is. So the example of ductile material is the metals. If, for example, you take aluminum, gold, silver, or stainless steel, so you can draw the materials, the frozen materials into a wire, or you can convert them into some particular shape, which means the material readily undergo plastic deformation or the change in shape can be done with much less effort. Whereas the brittle material will not undergo plastic deformation, or the brittleness describes the property of a material that fractures when subjected to stress but has a little tendency to deform before rupture. So the brittle materials are characterized by little deformation, poor capacity to resist impact and vibration of load, and brittle material has high compressive strength and low tensile strength. So in a broader view, the ductile material will undergo plastic deformation without fracture, and the brittle material does not undergo plastic deformation, or it is having a less tendency to deform before fracture. If we apply load, the material has to fracture at the end. The material will fail at the end. But before fracturing, there will be a change in shape, or there will be the change in dimension of the material. So if you apply a tensile load on the ductile materials, so you can observe some elongation in its length, okay, in its longitudinal direction and as well as in the lateral direction. So in the longitudinal direction, you can observe the change in length, and the lateral direction, you can see the change in the diameter. So diameter will get reduced, whereas the length will increase. So this is the plastic deformation one can find in the ductile material under tensile load. So on the other hand, if we take brittle material, if we apply tensile load before fracture, there will be no plastic deformation. So the material will not elongate, but there will be no change in the dimension of the material. Okay. So it will fail catastrophically, which means it does not give you any kind of warning or symptoms before fracture. So that is why the brittle material is restricted to a static application. Okay, you cannot find the brittle material in a dynamic application or the tensile loading conditions. So we cannot draw brittle material into a wire. Okay. So it's not at all possible. So this is the stress strain curve for ductile and brittle material. So in the first curve represents the ductile material, and the second curve represents the brittle material. So this one is ductile and this one is the brittle material. Okay. So how one can say this particular curve represents ductile material and this particular curve represents brittle material. Okay. So this is where a third important property which come into a picture, that is called toughness. So toughness is defined as the ability of the material to absorb absorb energy up to fracture. So how much amount of energy a material could absorb till its fracture? Okay. So how to calculate or how to measure toughness of a material? Okay. So it's a very simple, there is a very simple way to measure the toughness of a material. Okay. So toughness is measured by calculating the area under the curve. Okay. So for example, I'm taking the first curve, that is a stress strain curve of ductile material. So I'm just connecting a fracture point with the x-axis. So I'm just draw a vertical line up to x-axis. Okay, so now I'm getting a area. Okay, so this is a closed entity. So if you measure the area of this particular under the curve, you will get the toughness. Okay. Similarly, the brittle material. Okay, so this is a brittle material. So similarly, I'm joining a fracture point or the breaking point with the x-axis. So here also I'm getting a closed area. Okay, so this is a closed entity. So if you measure the area under the curve, you will get the toughness. So by comparing the area under the curves of ductile material and brittle material, so we can easily say, so which material has high toughness. Okay. So just compare, you can say the brittle material has less toughness, minimum toughness, and the ductile material has high toughness, which means before fracturing, before rupture, okay, the material absorbs more amount of energy. Okay, the absorbing energy is spent for the plastic deformation. So in the case of brittle material, it's not absorb that much amount of energy as ductile material. Okay. So there is no plastic deformation. So if the plastic deformation has to happen, it requires energy. Okay. So that's what happening in ductile material. It absorbs more amount of energy for plastic deformation, and the brittle material absorbs less amount of energy, and there is no plastic deformation. Okay. So the examples. Okay. The examples of ductile material and the brittle materials, or the ductile materials with metals. Okay. So the copper wires, you can see see copper wires and the aluminum wires, and you can see the gold chain and the silver chains. So these kind of materials are the ductile material. And one more important point is the ductile materials are always having FCC crystal structure. Okay, you can easily say whatever the metal that have the FCC crystal structure, okay, those materials will have the high amount of ductility. Okay, and the brittle materials, the examples of brittle materials are ceramic, ceramic materials and glasses. Okay, so the ceramic materials like aluminum oxide, silicon carbide, okay, silicon nitride, titanium carbide, tungsten carbide. So those materials are comes under the brittle material category, because those material you cannot elongate the tungsten carbide or silicon carbide or aluminum oxide. So the brittle materials are good under compressive load. The ductile materials are good under the tensile load. So that is the main difference among them. So, and here you can see, you can clearly understand what is the ductility. So what is the ductile material and brittle material. So here you can see a ductile fracture and the brittle fracture. So this is a component. Okay. So we are going to apply a tensile load on it. Okay. So before applying the tensile load, okay, I'm just measuring its length. Okay, its length, that is called initial length. Okay, say Li. So this is the initial length. So I'm taking two types of material. One is the brittle material and the another one is ductile material. So both the specimens are having the same dimension. Okay. So first one is the brittle material. Okay, I have applied a tensile load. Okay, the material has failed. Okay, there's a fracture takes place, and this is a brittle fracture. So brittle fracture always takes place perpendicular to the direction of applied load. So I'm applying load in the longitudinal direction, and fracture occurs in the lateral direction. There is a 90 degree to the axis of the material. Okay, and if you after fracturing just join those two pieces, and if you measure the length of the fracture surface, okay, that was joined, okay, so and if you measure those length, okay, that is a final length. Okay, so initial length before fracturing and final length after fracturing. So if you compare those two lengths, okay, there will be no change in it. Okay, so the initial length is equal to final length. So this is for brittle material, because the brittle material does not undergo plastic deformation, or there is no change in length or change in dimension. Okay, that is brittle material. And the second material, okay, that we have is ductile material. And if we apply the tensile load on ductile material, okay, before fracture, okay, it will undergo a plastic deformation. First, it will undergo elastic deformation, followed by plastic deformation. So what is elastic deformation? See, I'm having a material. Okay, so I'm applying a particular amount of load on the material. Okay, say I'm applying tensile load on it. So up to a particular limit, the material, okay, if you remove the load, okay, I'm applying the load, and now the material is under stress. Okay, there will be a stress. Okay, so if I remove the load, the material will come into its original shape. That is elastic deformation. If you apply load, it will undergo deformation. Okay, deformation. If you remove load, it will come into the original shape. It regain its shape. That is elastic deformation. So up to a particular limit, okay, the plastic deformation starts. So in most of the material, the plastic deformation starts at the yield point. Okay. So in the plastic deformation, the material undergo the permanent deformation. Okay. Even after you remove the load, the material will not come back to its original shape. Okay, that is plastic deformation. Okay, so plastic deformation will happen. Then finally the breaking, fracturing will take place. Okay, so before fracturing, there will be elongation in the ductile material. Okay, so after fracturing, we just measure the length of the fractured component. Okay, so say this is the LF. Okay, final length. Okay, here in the ductile material, the LI, the initial length, will not be equal to the final length. So the final length is always greater than the initial length, which means the ductile material has undergone plastic deformation. Okay, and here you can see the area under the curve is called as the absorbed energy, or you can say the toughness of a material. So the ductile material always have high toughness, and the brittle material always has the minimum toughness or the low toughness. Okay. So here you can see the ductile versus brittle. So I have given a properties into a table. So the first property is, so the first point is the ductile material can be drawn into wires by stretching. Okay, by applying a tensile load, we can will be able to convert the shape into wires or plates. Okay, in case of ductile material, whereas in the brittle material, okay, it does not undergo plastic deformation. So brittle materials break, crack, or snap easily. So there will not be any plastic deformation in brittle material. And the ductile materials show deformation. That means the elongation kind of thing. Whereas in the brittle material do not show deformation. Okay, it will fail straight away. Okay, there is no plastic deformation, there is no change in length, or there is no change in diameter, there is no change in dimension or shape happens in ductile brittle material. Okay, then ductility is affected by temperature. Okay, if you increase the temperature of a ductile material, okay, then its ductility will increase. Okay, in case of brittle material, it is affected by the pressure or the compressive stress. Okay. In the major examples for ductile materials are metals, okay, say aluminum, copper, gold, silver, platinum, lead, tin. Okay, so all are ductile material because you can convert those materials in the form of wires. Okay. And the examples of brittle materials or ceramics and glasses. If you apply the load, it will fracture into many pieces. Okay, so you cannot convert them into the wires or the plates on applying the stress. Okay, so hope you all understand what is ductile material and what is brittle material. Thank you.